Hey, hi. So this is the agenda for this week. First, we want to show that the cosets, how the cosets of a subgroup might not have a quotient group structure. And specifically, we'll do the example of G is S3 and H is the subgroup generated by 1, 2. And then we'll do example 13 on page 179, which is again about cosets and quotient groups. By the way, quotient group means the same thing as factor group. It's just the terminology that I'm used to. I think it's the more common term. And then we'll show that the commutator of O2 and O2 is SO2. Okay, so point 1. First of all, H is equal to, I'll color code the cosets. So H is equal to the identity and 1, 2, because the transposition 1, 2 has order 2. So it just generates a subgroup with 2 elements. Okay, now what are the cosets? So just randomly multiply H by elements on the left and see what you get. So let's try 1, 3 times H. Well, you just multiply each element by 1, 3. So it'll be, well, 1, 3 times the identity is just 1, 3. And 1, 3 times 1, 2. So 1 will go to 2, 2 will go to 3, and 3 will go to 1. So that's one coset of H. And then notice that because 1, 2, 3 is in this coset, if I did 1, 2, 3, I would have got the same thing. So 1, 2, 3 times H is the same thing. And also I should maybe write above 1, 2 times H is the same thing as H, right? Any subgroup, if you multiply it by on the left by an element of the subgroup, you'll just get the subgroup back. And then the final coset will be given by 2, 3 times H. I already know what elements it's going to contain. It's just going to contain the rest, but just to be safe, I'll actually compute it from scratch. So there's 2, 3, and then 2, 3 times 1, 2. So 1 goes to 3, 3 goes to 2, and 2 goes to 1. And if I did 1, 3, 2 times H, I would have got the same thing. So 2 elements in the same coset, they will give you the same coset, as obvious as that statement sounds. So this is the same thing as 2, 3 times H. Okay. Now, what you should think of these cosets as equivalence classes, mod H. So you're used to working like mod N. The idea of a quotient group is you're working mod a subgroup. And these are equivalence classes. So we have the identity equals 1, 2. We have 1, 3 equals 1, 2, 3. And we have 2, 3 equals 1, 3, 2. This is mod H. Okay, and then so a quotient group structure means that multiplication preserves equivalence, mod H. This is already second nature to mod N. So you already know, like, you're already comfortable presumably working mod n. Like, you know, you can add and subtract and stuff, and it'll preserve being equal mod n. So for example, like, I don't know, 2 is equal to 32 mod 15. So example, 2 equals 32 mod 15. That's, what's another one? 17 equals, no, I don't want to do 2 again. So let's do 19 equals 49 mod 15. And then you could look. So 2 plus 19 is 31. And 32 plus 49 is 81. And these are equal. Mod 15. That's the whole idea behind a quotient group, is you have some notion of equivalence and you want that notion to be preserved when you add or when you perform your group operations. And like I said, you're already used to that, mod n. So 2 elements that are equal mod n, if you add them, they'll still be equal mod n. If you invert one, they'll still be equal mod n. So every group operation makes sense mod n. And the idea is now, like, do we have a group operation mod H? These, we have the equivalences based on the cosets. Are these preserved by the group operations? So an answer is no. So the question is, are the equivalences given by our cosets preserved by group operation? And no, it's not, because let's see. Let's do a random one. Let's do the identity times 1, 3. Okay, so identity times 1, 3, easy enough. It's just 1, 3. What about 1, 2 times 1, 3? 1, 2, again, it's supposed to be equal to the identity, right? Because we're quotienting out by H. So this should give me, again, something equal to 1, 3, right? The equivalences should be preserved when I do my group operation, like it is mod n. But is it? So 1, 2 times 1, 3, 1 will go to 3, 3 will go to 2. So it's actually 1, 3, 2, which is in the green coset. So these are not equivalent. So even though these are equivalent, the identity and 1, 2 are equivalent, and 1, 3 is obviously equivalent to itself, the products are not equivalent as cosets. So we don't have a valid group operation. It doesn't preserve, operation does not preserve equivalence. And if you want to write it, so right now I'm kind of omitting the cosets. I'm speaking more intuitively, like what you want is this. But if you wanted to write it more formally, you should write the cosets in here. So you could write, so now I'll write it more formally. So ID times H is equal to 1, 2 times H. And obviously 1, 3 times H is equal to itself. But their product the products don't work out. They're not equal. So 2 equal elements should have the same. If you have pairs of equal elements, the products should be equal. So clearly something does not, you can't define a valid product on the cosets. I guess what I'm doing right now is not more formal, but I mean, you can kind of think of the cosets as being your elements, or you can think of the original group elements. So in the above, I was thinking of the group elements of S3 and just multiplying them. And I was just talking about what cosets they belong to, or you can just work directly with the cosets and it's really equivalent. So whichever one you're more comfortable with. Like you can think of group elements and think of them as being equivalent mod H. Kind of, that's what you do in modular arithmetic, right? Like you don't think of the set of all elements 1 mod n, right? You just think of 1 is 1 mod n plus 1 is 1 mod n, and so on. So you can do that the same in quotient groups. So you could just think of the elements of G, but now they're considered mod H. Or you could just think of the cosets directly. And there's advantages to both approaches. Okay, but yeah, so in terms of cosets, we have these two equal cosets. We're multiplying them, pairs of equal cosets, but their products are not equal. So we don't have a valid multiplication on the cosets. Let me do another one. So let's do 1, 3 times 2, 3. So 1, 3 times H it's equal to 1, 2, 3 times H. And obviously 2, 3 times H is equal to itself. But are their products equal? They should be, because products should preserve equality. But let's see. So 1, 3 times H, 1, 2, 3 times H. And then here's 2, 3 times H. Again, 2, 3 times H. So what is 1, 3 times 2, 3? So 1 will go to 3, 3 will go to 2, and 2 will go to 1. So it's 1, 3, 2. And is it 1, 3, 2? 2, 1 goes to 3. Yeah. Okay. And then what is 1, 2, 3 times 2, 3? So 2 will go to 1, 1 will go to 2. So it's just 1, 2. So again, we get different cosets, so the product doesn't make sense. And again, you can think of it in terms of cosets, or this whole thing I just wrote, I could have said 1, 3 and 1, 2, 3 are equal mod H. But when I multiply them by 2, 3, I get two things that are not equal mod H. So it's not like modular arithmetic. So modular arithmetic should be like the gold standard in your mind of how a quotient group should work. Okay. Let's do example now 0.2, whatever it was. Oh yeah, example 13 on page 79, 179. Okay, example 13 is we want to look at, we're going to let G be U of 32, so the units mod 32, which is just all the odd numbers because 32 is the power of 2. So it's going to be 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, 31. And then H is the subgroup generated by 17. Note that 17 squared equals 289, which is 9 times 32 plus 1. So it's 1 mod 32. Therefore, H is just 1 and 17, right? So 17 has order 2. So if the subgroup it generates, if you take all the powers of 17, you just either get 1 or 17, mod 32. Okay, so those are elements. And then what we want to determine is, we want to determine which group G mod H is. What I mean by that statement is they're kind of like default groups, and you want to see, you know, there's standard groups that are named. This is not one of them. And you want to find one of the standard groups that this is isomorphic to. But specifically because it's abelian, there's a theorem that says every abelian group is isomorphic to some standard abelian group. But I'll talk more about that in a second. So first of all, why is it abelian? G mod H is abelian. Why? In general, if G is abelian, okay, first of all, I should backtrack. Why does G mod H make sense? So since G is abelian, H is normal, every subgroup of an abelian group is normal. Therefore, G mod H makes sense. I mean, what I really mean by that is the thing that happened here won't happen. Whenever you take this issue that we saw with our example, where you don't get a group structure on the cosets, that only happens when H is not normal. It precisely happens when H is not normal. So the H we took before wasn't normal. And if it is normal, that won't happen. And that's the case in any abelian group. So every subgroup of an abelian group is normal. So whenever you have an abelian group, you can always form a quotient. And in any abelian group, for any abelian group G and subgroup H of G, G mod H is abelian. Why? I mean, the idea is G mod H, like I was saying before, you can think of it as it's really just G. I even just called it G mod. Yeah, like it's really just G mod H. Like it's the elements of G, when you're multiplying them, you're just having this extra equality that you're considering, which is whether two elements are equivalent mod H. But the multiplication isn't changing. It's like, you know, what you see, and again, the gold standard is a modular arithmetic, right? Like when you do 1 plus 17, or I don't know, like 23 plus 17 mod something, you really do find 23 plus 17 is 40, but you just maybe reduce it. It's the same thing here. So like the group operation is not changing in some sense. It's just being, you're just making some elements equal to each other now. So since the original group was abelian, the quotient should be 2. And you can verify this very quickly with a formal argument. So so the proof is for A and B in G, AH times BH is equal to ABH, which is equal to BAH because G is abelian. And then BAH is BH times AH. But I think it's clear, I don't know, it depends how you think, but if this is unclear to you, maybe think of the other interpretation, which is that G mod H is G, but you just have this extra mod H. So the operation is really not changing. It's just some elements are equal now. It's what you see with modular arithmetic. So like when you add mod n, it's not that addition changed. It's just that now, like if you're working mod 3, 1 and 7 are equal, but still like 2 plus 5 is still 7. It's just now it's equal to 1 as well. Same thing here. So making things equal doesn't change abelianness because already the product was commutative. So if you make more things equal, it doesn't change anything. Okay, so we know our G mod H. So back to our G and H. We know G mod H is abelian because U32 is abelian, right? The operation on U32 is multiplication, which is abelian. So we know it's an abelian group, and we know that it has 8 elements. So U32 has 16 elements, and H has 2 elements. So there are 8 cosets of H, hence G mod H has 8 elements.
Okay, just repeat this.
Sorry about that. The internet just disconnected for a second. Okay, so G mod H has 8 elements. And then there's a theorem that you're going to prove in chapter 11. I'm guessing you're allowed to use it though now, since the textbook is using it for this example, which basically says that, if you try really hard to think of abelian groups, there are some obvious choices, which are products of cyclic groups. So every cyclic group is abelian, and the product of 2 abelian groups is abelian. So products of cyclic groups are all abelian, and then you wouldn't be able to find any more. And then there's a theorem that proves that's the case. So any abelian group must be isomorphic to a product of cyclic groups. So G mod H, there's only 3 options for it because it's abelian. So hence, by the classification theorem, for abelian groups, G mod H is isomorphic to either Z8, Z4 plus Z2, or Z2. Right, so these are the products. These are the possible products of cyclic groups containing 8 elements. Okay, so now we want to figure out which one it is. To do so, we should first write down the elements of G mod H, so the cosets. Okay, so there's H, which is just 1 in 17. There's 3H, which is, so you multiply 1 in 17 by 3, and then you'll get 3 and 51, which is 19, mod 32. And then there's 5H, which is, do the same thing, so you get 5 and 85. 85 mod 32 is 21. You keep doing that, so you get 7H is 7 and 23. 9H is 9 and 25. 11H is 11 and 27. 13H is 13 and 29. And finally, 15H is 15 and 31. Now you could keep going, but you would just keep getting back cosets that I already wrote. So if I did, for example, 19H, I would just get back 3H. So these are all the elements. So first of all, there is indeed a valid group structure on these cosets, right? Like you can check it. For example, 3 times 13 is 39, which is 7 mod 32. And then what about 19 times 13? Well, God, I have to do some mental math. So 247 mod 32. Oh my God. 247 mod 32. 7 times 32 is 224. So it's 23. Ooh, works. Okay, so yeah, they're in the same coset, right? So I took 2 different products that should have been equivalent, and I got equivalent elements out of it, or alternately in terms of cosets. So 3H times 13H is 39H, which is 7H, and 19H times 13H is 247H, which is 23H, and these are equal as we expect. So I already proved to you that it has, this is not a proof that it has a group structure, but we expect it to, and it's good to check maybe that and see that our abstract reasoning does actually work. Okay, now, how do we figure out which abelian group it is? So the way to separate products of cyclic groups from each other, so to tell them apart, you look at the orders of the elements. So let's look at Z2. So let's look at Z8. There's 0, 1, 2, 3, 4, 5, 6, 7. This has order 8. This has order 4. This has order 8. This has order 2. This has order 8. This has order 4. And this has order 8. And I mean, this is the identity, so it has order 1. Now, Z4 plus Z2 does not look like that. So we'll look at it. So Z4 plus Z2, there's the element 0, 0, which again is the identity. So it just has order 1, not very interesting. But what about 1, 0? So that has order 4. What about 2, 0? That has order 2. What about 3, 0? Again, order 4. And 4, 0. Oh, well, 4, 0 is just 0, 0 because it's Z4 plus Z2. So, but then we can take 1 in the second coordinate as well. There's 2 elements of Z2. So we can have 0, 1, and this is order 2. We can have 0, 2, which has, oh, and it's 1, 1, which has order 4. We can have 2, 1, which has order 2. And 3, 1, which has order 4. So there's a difference between the 2 groups. You can tell it in the orders. The group Z4 plus Z2 has 4 elements of order 4 and 3 elements of order 2, whereas Z8 only has 2 elements of order 4 and 1 element of order 2. And Z8 has elements of order 8, which Z4 plus Z2 doesn't have. Okay, what about Z2 plus Z2 plus Z2? This is also way different. So 0, 0, 0, again, order 1, it's just the identity. But what about 1, 0, 0? That's order 2. What about 0, 1, 0? I mean, what about 0? Yeah, 0, 1, 0. Just thinking what orders to do them in. I'll just do them in a random order. That has order 2. 0, 0, 1, 1, 0 has order 2. 0, 0, 1, order 2. They all have order 2 because it's just Z2 in each coordinate. So as soon as you add it to itself, you get 0. Only the identity has order 1 because it's just already equal to the identity. So we get 1, 0, 1, it's order 2. And then 0, 1, 1, order 2. 1, 1, 1, order 2. So this one was obviously different from the other ones. It just only has order 2 elements. Okay, now let's look at our elements and figure out which one we have. Okay, so let's look at 3H. 3H squared is 9H, which is not equal to H because 9 is not an element of H. Okay, what about 3H to the power of 4? We know the order has to divide 8, so I don't even need to check 3H cubed. Okay, so 3H to the power of 4 is 81H. Mod 32, 81 is the same thing as 17. So it's 17H. And then 17 is equal to 17H is equal to H because 17 is an element of H. Hence, 3H has order 4. Immediately, we know that G mod H is not isomorphic to Z2 plus Z2 plus Z2 because that only has elements of order 2. Okay, now let's look at 5H. But we still don't know which one it is because there's still 2 options left. Okay, so what about 5H? Okay, 5H squared is 25H, which is not equal to H because 25 is not an element of H. What about 5H to the power of 4? So it should be 625H. What is 625 mod 32? Oh God. So it's 640 would be multiple of 32. So this is 17. Good. So it's 17H, which is equal to H because 17 is an element of H. So 5H has order 4 as well. We still don't know which group it is though, because both Z8 and Z4 plus Z2 have at least 2 elements of order 4. But we'll just keep chugging along and hopefully we'll notice a difference between them eventually. We'll find something that tells us which group it is. Okay, so 7H squared is 49H, which is 17H, because 49 really means 17 mod 32, and 17H is equal to H because 17 is an element of H. So 7H has order 2. Still, we don't know what group we're in because both Z8 and Z4 plus Z2 have, where is it? Oh my God. Oh, here it is. They both have an element of order 2. What about 9H? So 9H squared is 81H, and 81 mod 32 is the same thing as 17 again. So 9H has order 2, and now we found our difference. So since G mod H has 2 elements of order 2, G mod H is not isomorphic to Z8 either. Right? Because Z8 only has one element of order 2, which is 4. So we know that G mod H must be isomorphic to and this is a nice proof because we could, I mean, theoretically find the isomorphism directly. And it wouldn't even be that hard. I shouldn't say theoretically. I mean, you could definitely do it. But because we have a powerful theorem that tells us what every abelian group looks like, we don't actually have to find the isomorphism. We just have to rule out the two other options it could have been. And then we automatically know it's Z4 plus Z2, even though I didn't even tell you what the isomorphism is. But you can figure it out. Okay. And then last thing, we want to find the commutator of O2. Commutator subgroup. Or actually, we want to show it's equal to SO2. Okay, so recall that the G commutator G is the subgroup generated by elements of the form A, B, A inverse, B inverse, where A and B are any elements of G. So you look at all those elements, you make a subgroup out of them. So initially it might not be a subgroup, but you can just take their products. You know, like you've talked about subgroups generated by a set, right? Like if you start with a set, you can always enlarge it until you have a subgroup. Just keep taking products, keep taking inverses. Eventually you'll have something closed into products inverses. So that's what the commutator subgroup is. And so we'll look at the commutators. So recall the elements of O2. O2 consists of rotations and reflections. Our notation will be as follows. So R alpha will denote the rotation by alpha counterclockwise, while F beta be the reflection through the line, making an angle of beta with the positive x-axis. I'll draw a picture. So that's the line I'm talking about for F beta. Okay, so there are four kinds of commutators, right? Because there's two kinds of elements in G. So there's four kinds of commutators you can get. One is of the form R alpha, F beta, R alpha inverse, F beta inverse. Two is F beta, R alpha, F beta inverse, R alpha inverse. So first is rotation and reflection. Second is reflection and rotation. Third is just two rotations. So R alpha 1, R alpha 2, R alpha 1 inverse, R alpha 2 inverse. And you know, I can immediately say what the third case is going to be, but I'm just speaking without further thinking right now, just saying what are the four cases, and I'll analyze the four cases. But of course, like maybe you can immediately see that 3 is just going to be the identity because rotations commute with each other. So rotating negative alpha 2, then negative alpha 1, then alpha 2, then alpha 1 will just get you back to where you started. Okay, and then 4 is two reflections. So F beta 1, F beta 2, F beta 1 inverse, F beta 2 inverse. Okay, so for one, here's a useful fact. For any rotation R and reflection F, F inverse equals R inverse. The idea is, I guess, you reflect and then you rotate and then you reflect back. And then since you rotated while you were reflecting, you really made everything go in the opposite direction, right? Like you reflect and then you rotate by alpha. But since you rotated while everything was reflected, you really made everything rotate by negative alpha. And then when you reflect back, that's the total effect it'll have. Everything will just be rotated by negative alpha. I encourage you to draw a picture. Unfortunately, I don't have enough time to do that, but yeah, if you don't get that, then draw a picture or just memorize this. There's not that many facts you have to memorize there's not that many facts I think that show up over and over again. Like there's this one and there's one more I'll use when I'm doing the product of two reflections. So, okay, so we're using this fact, R alpha, F beta, R alpha inverse, F beta inverse equals, so I'll isolate the thing I want. It's that, and then using the fact, I get it's R alpha times R alpha inverse, so it's just R alpha times R alpha, which is R2 alpha. Okay, so that covers case one. Case two, F beta, R alpha, F beta inverse, R alpha inverse. This is just the inverse of case one. So note that F beta, R alpha, F beta inverse, R alpha inverse is just the inverse of R alpha, F beta, R alpha inverse, F beta inverse. It's just the inverse of that. So we already know what it is based on case one. So it's R2 alpha inverse, and so that's R negative 2 alpha. So hopefully you can get an idea of what it looks like when you inverse a commutator. This is exactly what happens. So it's just like a commutator splits into two groups of two, and it's like in each group they flip. So R alpha F beta becomes F beta R alpha, and same thing for the inverses. Okay, so we found 2, 3, like I said. So we have R alpha 1, R alpha 2, R alpha 1 inverse, R alpha 2 inverse. Since rotations commute, this is just equal to identity. So that case is easy. Lastly, it's reflections. So F beta 1, F beta 2, F beta 1 inverse, F beta 2 inverse. First of all, an inverse of a reflection is just itself. So really, this is just F beta 1, F beta 2, F beta 1, F beta 2. Now, again, useful fact. F beta 1 times F beta 2 is R2 beta 1 minus beta 2. Remember that the notation I'm using is I'm referring to a reflection by the angle its axis makes. It's the axis of reflection makes with the positive x-axis. So that's why I can write beta 1 minus beta 2. It depends on the notation you're using. But for me, beta 1, beta 2 are angles. And this is something you proved in class. So you showed that the product of two reflections is a rotation by twice the angle between the lines of reflection, the axes of reflection. Okay, so I can write this as R2 beta 1 minus beta 2 times R2 beta 1 minus beta 2. So I get R4 beta 1 minus beta 2. Okay, and this is all I need. So to actually do the proof now, we showed that every commutator is a rotation, right? We got a rotation in every case. We got the identity in case 3, but that's also a rotation. So then, since the commutator subgroup, so a commutator is just the elements, right? These f beta 1, f beta 2, f beta 1 inverse, f beta 2 inverse. That's a commutator. The commutator subgroup is a subgroup generated by the commutators. So since this is generated by the commutators, it follows that O2 is generated by rotations. Since every commutator is a rotation, hence it must be contained in SO2. This SO2 is called subgroup of rotations. So since this subgroup is generated by rotations, it must be contained in the subgroup consisting of all rotations, right? Because it's generated by rotations. Okay, so we proved one direction. For the other direction, recall we showed that R alpha, F beta, R alpha inverse, F beta inverse is R2 alpha. So any rotation R theta can be written as R2 alpha, namely, just take alpha to be theta over 2. Therefore, every rotation can be expressed as a commutator and so every rotation is in the commutator subgroup. And so we have equality. All right, that's all we have time for. Thank you for listening. Good luck on your term test.